Chapter 21, Polymers. This is the chapter about plastics, polymerization, how polymers form. And there's three different major polymerization type reactions. It can either be free radical reaction, it can be run by a positive ion with a cation, or it can be a negative ion, an anion that pushes the polymerization. So macromolecules are very large molecules consisting of repeating units. Each of those repeating units is a monomer. And these can be natural or these can be synthetic. Plastics are synthetic. But natural macromolecules are like glycogen. Glycogen is a polysaccharide in people's liver. The monomer is glucose. Glycogen is a macromolecule consisting of repeating glucose units. And in plants, it's starch. Again, glucose units. Cellulose is a different type of polymer with glucose units, but the bonding is different, so most organisms can't consume it as food, so cellulose ends up as a structural material. So we build things with wood because most things cannot consume wood as food. Polymers are large molecules. Again, poly comes from the Greek word many. Monomer is the repeating unit. And a plastic is a variety of any of these polymeric substances. Polymers can be natural or synthetic. Cotton is a natural cellulose polymer. And again, cellulose is a polymer made out of glucose. The difference between cellulose and starch is that starch is edible because of the type of chemical bond in the glucose. Most organisms can break it down into glucose, and then the 10 enzymes of glycolysis will break it all the way down to energy. And pyruvate. And then the pyruvate can go into the mitochondria through the citric acid cycle and the electron transport chain, and it can be completely broken down to carbon dioxide, which you'll breathe out, and you can extract that energy. Cellulose, like cotton, is not food because most organisms don't have the enzymes necessary to consume that as food. And so at the end of the day, what's food or not food depends on what enzymes an organism has to decompose certain chemicals. For example, termites do eat wood. Termites have a protist in their stomach, and that protist harbors a bacteria. And in that bacteria, it produces the enzymes necessary to break down cellulose bonds. And so now a termite can consume wood, and they'll break it down to its glucose monomer. So to a termite, wood is no different than a potato. It's just a big glucose polymer. Polyethylene. This is a polymer of between 2,500 and 25,000 ethylene units. And the monomer is ethylene. And here we see ethylene. Here's our beginning monomer. And with the catalyst, it reacts, and we get repeating polyethylene units. Classification of synthetic polymers. This is based on their properties and their usage. There are rubber-like materials or elastomers that have more elasticity. Elasticity is how far can you distort a material and it comes back to its original shape. Flexible films, synthetic textiles and fibers, resins or plastics that can cast and mold things, coating resins, and then miscellaneous polymers like hydraulic fluids, foam insulation, ion exchange resins. A big explosion in material science is due to our ability to make many new synthetic polymers. And classification of polymers. We can have an addition polymer, which is produced by successive addition reactions, like polyethylene. There can be a condensation polymer. Monomers combine and eliminate some sort of substance, like nylon. And nylon's a cool one. We run that one in lab. You have your chemical reaction, and there's two liquids because one of the chemicals is dissolved in water and one is dissolved in hexanes, which is an organic solvent which it forms a layer on top of the water. And then the actual nylon forms where the two liquids touch each other. And so you see a film develop there. Nylon, NY is for New York, LON is for London. We had two chemical teams that teamed up and made one of the world's first synthetic compounds. Thermoplastic polymers, they soften when reheated, and you can reshape them. Thermosetting polymers, they're infused solids and do not soften when reheated, and so you can't soften them and reform them into something new. And so some plastics can be heated and reset, and some cannot. That just destroys them. So what is the difference between addition polymerization and condensation polymerization? During condensation polymerization, the polymer is formed in addition to water or some other small molecule. In addition polymerization, only the polymer is formed. So in an addition polymerization, here we're going to see a free radical mechanism with ethylene. And so basically, this electron travels here, and this electron travels there, leaving a free radical here. And then, if this one bumps into another ethylene, it'll go here, and then another ethylene with its double bond. One electron will go there. And this is characteristic of free radical reactions. Single electrons are moving. So a single unpaired electron is a free radical, and that is characteristic of free radical reactions. And so basically when we polymerize through free radicals, we have free radical formation, and then a propagation, and then a termination. So first, like we saw before, you need to initiate free radicals. Peroxides are really useful because the peroxide bond is very weak and breaks apart into free radicals pretty easily. That's why benzoyl peroxide is used medically, like on acne pads, because the free radicals are damaging to bacteria on people's faces, which cause acne. And so then the free radical does a free radical reaction. It extracts one electron from the double bond, forming this chemical bond here, and leaving a free radical here. And now this will hit another ethylene, and the same thing will happen. And we can do that over and 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 over again. As we saw, polyethylene was typically between 2,500 and 25,000 basic repeating units. So this happens thousands and thousands and thousands of times until, through sheer luck, there's termination. Two free radicals meet up and quench, and the reaction is done. And this is one thing that plastic chemists focus on, is conditions, because this is a very hard to control reaction. And so if you're trying to make a polymer of a certain size, conditions are extremely important. Basically all of your control comes into your conditions. Your pressure, your temperature, what solvent is there, how long does it react. All of that is finely tuned to make the plastic that you want to make. And what are some common uses of polyethylene? Well, packing materials, molded articles, plastic films, garbage bags, grocery store bags, flexible bottles, containers, and toys. And so here, we go to polypropylene. Propylene is another way to say propene. And again, there's a double bond. It is an alkene. And we have the same type of reaction. So you have the reaction gets initiated, you have a free radical, and then you keep adding successive polypropylene units. So here's a polypropylene, here's a polypropylene. And again, we'd use the same type of molecule to initiate the reaction. We'd have a little bit of a peroxide or something. So you'd start with your initiator. And then again, that would form your first bond. So that gets it kick-started. This won't happen without that. And then you have your free radical here. And then that will attack your next polypropylene. And so you form that new carbon-carbon bond. You have a free radical here. And you just keep adding polypropylene after polypropylene after polypropylene. And again, we do this thousands and thousands and thousands of times to produce polypropylene. So addition polymers are the most common of all plastics. They're relatively easy to produce, and over 50% of all polymers in the United States are made from ethylene or their related compounds. 15% of all landfill material is plastic, and that's too bad because it actually takes 500 years for these plastics to degrade under normal circumstances. And so once plastics are in a landfill, they stay there for 500 years. In the United States, about 30 million tons of plastics are thrown away each year. And so there's a lot of pollution with plastics. Unlike glass, it's not just silica. So glass eventually Glass bottles can be recycled. A lot of states will give you 5 cents back to force people to recycle them. But slowly over time, they'll wear down back into sand too. Like sea glass is common for vacationers to collect. Because once it gets in the ocean water does chemistry to it and becomes really smooth and really rounded. And it's actually kind of pretty to find sea glass on the beach. Metals have an intrinsic value. All different metals have a certain worth, like iron has a certain value depending on the market, copper does, aluminum does. And so metals aren't just thrown away and forgotten about because they're worth money, and people, scrap metalists will collect that and retrieve that value. But plastics, there's no money to be made in recycling plastics, which is difficult, and which is why they get thrown away with such abandon. These codes that we see on plastics tell us about the density, because at a recycling center, densities are important. There was just a new invention which kind of addresses this, but before the newest round of technology, if you had different plastics of different densities, it would gum up the recycling machinery and it wouldn't work well. And so you first had to sort plastics into the correct density categories before you could recycle the plastics, which made recycling plastics really expensive, actually. And so that was another problem with plastics, is in general it's cheaper to make brand new plastic than it is to recycle old plastic. And so there's not a lot of economic incentive to recycle old plastics. And so again, a lot of states put deposits on pop bottles to force people to come back and recycle their pop bottle to get their nickel back. But all in all, because it's cheaper to make new plastic than recycled plastic, a lot of plastic is not recycled. And again, here we see the density codes, 2, 3, 4, 5, and 6. 2 for high-density polyethylene, 3 for polyvinyl chloride, PVC, 4 for low-density polyethylene, 5 for polypropylene, and 6 for polystyrene. Recycling rates, again, super low. Less than 30% for all types of plastics here, because there's no economic incentive. And so when a municipality like a city is low on money, one of the first things they might stop doing is recycling plastics because it's expensive. It's good for the environment, but it does cost money. And that is one of the struggles of plastics and why we're slowly trying to get away from using plastic things, because especially in the oceans, pollution is becoming a really big problem. There are entire mountains of plastic garbage floating in the ocean, and that is becoming a real pollution problem on Earth. So PP, here we have polypropylene. PS, polystyrene. A diene has 2 double bonds, so it has 2 carbon-carbon double bonds. And this is another type of addition polymer. 2-methyl-1,3-butadiene is isoprene, and that is the basic unit of rubber. Rubber is produced from isoprenes. And so when isoprenes polymerize, they form this rubber chain, polyisoprene. When butadiene polymerizes, it forms this butadiene polymerization chain. So these are unsaturated plastics. Before, with polyethylene and polypropylene, we didn't see any double bonds in the final plastic product. But here we do. And your PowerPoints don't do a good job of showing you why you get that double bond, so let's work one through. If I start with butadiene, here is butadiene. And now we start with some sort of molecule for, it can either be positive ion or negative ion. So let's say you use the negative ion, or it could be either positive or negative. Both ways work. Different plastics choose what makes the most sense in that situation. So here we have 2 possibilities. Either a positive ion can initiate the reaction, or a negative ion will initiate the reaction. In the case of a positive, it'll draw 2 electrons from those double bonds to form a bond here. And then that will form a positive there. If that double bond moves and it's gone, you basically have formed this compound. Alright, so we have a reaction, those electrons move, and now we have this compound. And actually that quenched the positive charge here, so that basically that's not there anymore. So the positive moved from here to here, because these 2 electrons moved there, making a bond here, but now this carbon is missing 2 electrons. It has a positive charge, because that was that one electron it was claiming, the other one was claimed by the other element. So now the other 2 electrons move over. To form this molecule. So now that's why the double bond migrated one, because that positive charge. That pushes the positive charge over here, and now it will bind to another butadiene. So we see that there is another butadiene next to it. This is the second butadiene. The electrons from the second butadiene move, and basically we're having the exact same thing happen again. And that will happen over and over and over and over again. In the case of a negative charge catalyzing this, the electrons just move in the opposite direction. In that case, the 2 electrons from the negative charge attack here, they kick these electrons here, and this electron gets kicked here. So really just one electron is moving. So one goes here, one goes there, this one gets pushed here, this one comes here, and they have 1 extra electron, so your negative charge sits on this carbon, and this will attack another butadiene, 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 and this will attack another butadiene. And so it's propagating the same way, except it's a negative charge pushing instead of a positive. The negative attacks the next molecule. This will attack the next molecule. If it's a positive charge, it will attract the electrons. And so basically, your biggest difference here is the directionality of the electrons. With the positive charge, there's a positive coming in which is attracting electrons. In a negative charge, they're attacking. So in the positives, we see electrons getting pulled back. In the negative, we see electrons being pushed forward. And that's why that double bond is migrating in these cases. Copolymers. This is when we have 2 different monomers. So here we see butadiene, styrene, butadiene, butadiene. And here we see styrene and 1,3-butadiene in a 1:3 ratio. And this gives us SBr rubber, styrene butadiene rubber. Vulcanization is the process of putting in sulfur cross-links into rubbers, and this makes the rubber much, much tougher. This was important historically because this is what allowed a rubber to be tough enough to be used in car tires. And there's also carbon and stuff added to it, that's why they're black, but the vulcanization is the key part of why tires are so tough. This alters the physical properties and greatly increases abrasion resistance and increases the useful temperature range of the polymer. Without the vulcanization, the rubber melts at too low of a temperature, and you can't use them on tires because your tire just melts on the street. It didn't work. So this was absolutely essential, the process of vulcanization into rubber moving into the car tire industry. Rubber is a naturally white compound, and so pure rubber will look white. All right, and that is the end of part 1.